Pleasure to be here this morning. Let's jump straight into it then. I can see some tired faces here, and I think everybody's looking forward to a cafe pausa, amongst other things. So today I'm going to give some insight into how our piezo jets work from a fluidic level and show you a simplified working model that will allow you to make inferences for predicting and troubleshooting jetting issues. This simple model, which is based on a resonance circuit, is also used by our jet designers at the onset of new jet design and jet modeling. But as you will see, it's quite complicated. So a quick refresher on what Domatics does. We primarily build printheads that we sell to OEMs who integrate them into their own printers. In this case here, for the Samba head, which is what's shown here, which is our flagship MEMS product, we also sell to our Fujifilm jet press division. And what we see here is a flexo quality press. We also make material printers, and we have an integration division where we make custom built bars. Typically this is for adding a print station to an existing line, not really a standalone printer. New additions to our sales portfolio is the Samba jet press components business. This is basically the enablers or the building blocks within the within the jet press print engine itself. So it's a combination of hardware and software there that's available in the jet press configuration and size, but also in custom sizes, smaller or larger than the jet press itself. So this is where we are on the Inkjet technology map. We see the Inkjet is broken into either a continuous Inkjet family or drop on demand. All of these have their own pros and cons. For the piezoelectric, which we'll be focusing on today, there is the application of voltage to a piezo material to create an acoustic pulse. And this is similar to sonar. As I said, this is what we'll be focusing on today. So then, looking at the overall head structure, this schematic gives us a good understanding of what a modern piezo inkjet head with recirculation looks like. This is done in this manner really to kind of provide excellent care and feeding of the jet itself, which you can see kind of center bottom there. Within each of these structures itself, there are multiple bypasses and there are multiple manifolds, and all this helps with the priming of the head, the thermal management, and making sure that there is fresh ink being delivered in a consistent basis to the jet structure itself, and also to avoid any air there, and if it is in there, that it's removed from the jet as quickly as possible. So quickly then, talking about our MEMS process, which is in our fab in Santa Clara, of which, as I said, the Samba head is the flagship product. We start off with 3 silicon wafers, 2 silicon insulator and 1 blank wafer. And what we do then with these, as you can see, is that we pattern in the nozzle wafer, and then we create the fill and jetting and refill channels, both top and bottom, within the main wafer itself. And we put all of these together into a 3 wafer stack, and we use what we call fusion bonding. So basically everything that you see there is no epoxy in that stack itself, is fusion bonded. We heat up that stack to approximately 800 degrees, and the silicon at the atomic level, silicon oxide, fuses, creating the integral structure that you see there. What we do then is we grind off the handle off the membrane wafer, add the dielectrics, the piezo, and the contactor, and the metal electrode, and then we grind off the nozzle wafer itself, and at some point we apply the non-wetting coating. So within the MEMS fabrication itself, we call our jetting structure a die. And this is what we see as regards the mask of the structure itself. You can see the jets that are there. We also are depicting what the ink flow looks like there. The kind of the red part at the top is where the piezo is. You see the descender jet, the ink down there, the nozzles at the bottom, and you also see the recirculation feature very, very close to the nozzle itself. This jet, as you can see, runs at 220 kilohertz. That's what Samba is possible of. So if you do simple mathematics of 2048 jets in that very small 44 by 12 silicon region, what it means running at 220 kilohertz is per second it's firing 450 million drops. And that equates to approximately 25 milliliters of ink that is fluxed or jetted out of the head per minute. Excuse me. So in order to get to these type of high firing frequencies, it's really important that the jet is very, very, very small. And the key enabler within this process then is our sputtered PZT process. And what we mean by that is we have this unique process that's different to solid jet, different to bulk PZT, in that the PZT itself is poled as it's deposited. So it is in a natural poled state, whereas opposed to bulk or solid jet PZT, where they're trying to get to their natural unpoled state. What that gives us is huge reliability and excellent lifetime associated with that. Let's back up a little bit then and look at our legacy products. So these would be what would be considered S-class, Q-class, Starfire heads. And this is, if you want to look at this conceptually, is a very large jet. It's a long jet, it's a wide jet. And the operation, or the fluidic operation in relation to this is as follows. So when we apply when we apply a voltage to lift the PZT, as you can see there, we are also at that point creating acoustic pulses. And these acoustic pulses then move away to either side of the piezo material itself. What happens then is at that high impedance barrier there, where the jet is defined by the dotted line, the acoustic pulse on the left is reflected to the way it came. The other pulse is also reflected, but it's a smaller pulse because it's lost a lot of its energy to the meniscus itself. Take advantage of the resonance in the circuit so that returning large pulse on the left is under the PZT when you drop it, so that we take advantage of that pulse and the new pulse that's generated by dropping the PZT in order to get maximum energy out of that. And then that creates a much more efficient pressure wave, and that is converted into flow at the meniscus itself. So that's our non-silicon MEMS products. So we said the jet is determined by the travel time within the jet. It's not a priori 2 times the fire pulse width, but that is a very good starting point to consider. So let's kind of compare that jet that we just looked at to our Samba or our MEMS jet. So here we see the relative size and scale of the PZT and the jet structure itself. Both of these products are hugely successful, widely adopted and accepted within the market itself. Both are constructed using laminates, and in the case of the Starfire jet, this is done with using epoxy bonding. In the case of the Samba jet, this is done using fusion bonding, which I talked about earlier, and the sputtered PZT. So let's take a minute just to consider the sputtered PZT, because we see this as the key enabler in the whole MEMS structure itself. What we see here then, on the 2 features that might draw your attention to, is the main part of it there, as you can see, is the PZT, and the 2 kind of black and white layers at the top are the dielectric layers. The thickness of that PZT there is 3 microns. And what that means, and what's also significant, or I draw your attention to, is the density that's there in that. It's an incredibly dense structure, and you also see the kind of top to bottom graininess that's in there. So again, this is a consequence of the poling as deposited as we build up the structure, and from the bottom to the top, it's poled. So the graininess that you see there is ultimately reflecting the poling that's happening in there. And again, the being poled at its rest state allows us to have incredibly reliable PZT actuations. So ultimately what I'm trying to get at here is this type of structure and that scale of jet leads us to small, dense and thin structures that still gives us the deflection that we require at the really, really high speeds, up to 220 kilohertz in order to consistently create a pulse that gives a jet from that. So, you know, deflecting a PZT at that scale is incredibly beneficial to the printhead performance and the printhead operation. By comparison, depending on the native drop size of the starfire head, the relative PZT thickness of the starfire head ranges between 150 and 200. So, considering that scale again, now we're looking at the small Samba jet, which is not the large jet, and a different dynamic happens here. So this jet is short and it's narrow, and because travel times are fast in there, it's approximately the same pressure everywhere. There is not that large acoustic pulse and reflection going on in here. So that when we raise the PZT again by applying the voltage, the whole jet is, to all intents and purposes, the same pressure. In this case, it's a low pressure as we raise the PZT. That then the meniscus pulls back in to address and counteract that pressure change to get it back to its natural state. When we drop the PZT, we get a high pressure, and that then gets converted into flow energy and into drops at the meniscus itself. So how are we going to think about the jet as we look through the next couple of slides going forward? The way we would like to consider this is it's a system with a first resonance circuit to add energy, similar to what I showed on the non-MEMS there, and I'll show you why we still consider that to be the case. It has a nozzle feature that converts the flow to pressure, and the flow directs an ink stream, a drop is formed, and then we have a second resonance circuit that aids in the refill of the jet to refill the depleted ink that has been ejected from the printhead, from the nozzle at that point. So the two resonance circuits we're talking about, the jetting resonance circuit and the refill resonance circuit, which runs at about, or is designed to run approximately about a tenth of the jetting circuit. What you see here is just the fluid path in the Samba jet itself. There is no mechanics there. Everything there is just a cutout that shows how the fluid enters the Samba head, jets down, and then is returned there like that. So if we look at the jet circuit itself, this is bound by the black lines that we see here. And if you look at the refill circuit, resonance circuit, excuse me, this is bound by the red lines or the red parameters that we see here. And so, to all intents and purposes, this jet, which has elements of inductance and capacitance and does have resistance, but that's not important for jetting dynamics. We have a transmission line, excuse me, here, and then we can convert this to a lumped parameter using first order pi segments. So ultimately what we're doing here is making this a very simple resonance circuit in our assumptions. And you can say, well, that's all very well, but how does that work out in reality? This is the jetting montage then of the Samba jet. So what we see from left to right is the drop velocity, a measure of the drop velocity of the drop itself as we increase the fire pulse width from left to right across there. So at some point there, at the most, let's say the fire pulse width is in most resonance with the circuit, where the drop velocity is highest, and that is the furthest point there from the nozzle itself. So we have this simple curve which represents the simple structure that we're talking about, and we get this simple model that we can use and start to infer and anticipate jetting problems and troubleshoot jetting problems from. And if we take that, let's say that most efficient fire pulse width there on that resonance, and then we set that as a constant, and then what we're showing here is a montage of increasing firing frequency as we move from left to right. What you see here then, particularly in the point of the oscillation, is where the frequency is either in sync or out of sync with the resonance, the natural resonance of the jetting circuit itself. Where it is more in sync, you have a faster drop, whereas it is less in sync, you have a slower drop. And that's what the oscillation is accounting for there. Once the drop ends, it will be what it will be. And what we're showing here is a montage of two different inks. They have the same, it's using the same jet, they have the same drop velocity, they have the same ink viscosity, but you're getting two different outcomes there completely. One where you see on the top there is a short ligament which doesn't snap and catches up with the main drop, so you have a single drop, no aerosol, no spray there. The second ink, which has different surface tension, different densities, has a much different performance and a much different outcome, where the ligament stretches to the point where it snaps, and it creates two separate drops, and the trailing drop does not catch up with the main drop itself. So the specifics of the ink itself are really, really important under jetting conditions. And like I said, the jet design can't take into account any of this. This is where the ink chemists earn their bucks. So as regards the refill circuit then, once the ink has been ejected, and there is it needs to be, the drop has been ejected, what we need to get at that point then is it to refill and replenish to the mass of what has been ejected there. So the meniscus, when it is back in that position, is trying to pull back down into its natural position, and in doing so, it pulls, I'm calling them there, at the boundaries. If you look at the boundaries there again with the dotted line, it's pulling ink in from there. Now, you could say, well, why don't we make those boundaries bigger? But what we would do in order to help the refill process, what would happen in that case is, if we make them too big, we start to lose the jetting energy through the jetting cycle itself, and then we get a much different response. And what that would mean, like, is if we look at this, excuse me, if we look at this net flow, this is at a sensor at the nozzle itself, after we have pulsed here, you can see this is for the same jet construction, but just different inlet and outlet diameters there. We get a completely different response there as to how the flow goes and how it recovers eventually to become stable again. And what that means then is that has an effect potentially on the sustainability of the printhead under high performance, under high printing, excuse me. And when we're talking about failing frequency here, we're talking about failing for sustainability. So we're getting missing jets, crooked jets, jets out, things like that at those firing frequencies. So if the damping ratio is too high, we end up with not being able to refill the head in time, and that leads to, excuse me, that leads to sustainability issues. What that looks like, or what we believe is happening in these cases, is the ligament that's there before it kind of snaps off and either joins the main jet or continues to stretch as the jet moves away from the nozzle. At some point, it does not become centered on the apex of the meniscus itself. And what that looks like in reality, if we were to look at it, is you can see a lot of jets there, main drops with crooked ligaments behind it, and that pulls the jet to one side and deviates it off its intended path. Ultimately, what that means is white lines, white spaces, both in the process and the cross-process direction. So that pulling to the side can happen anywhere on the perimeter. Here it's just shown to the right, but it could be anywhere, so that's why you get process and cross-process directionality issues associated with that. So our modelers and Dymatics towers would like you to know that despite this being a simple concept, there is a lot of parameters that need to be taken into account here. So they're named collectively as scales, domains, and outputs, and those are the type of subsets of those. In the case of domains, mechanics means the stress and strain on the silicon in the silicon MEMS head itself. So here what we see is that's taking the previous slide and converting it into to other attributes of, it's better to read it here, dimensions, material properties, and functions. So basically dimensions is pretty much what it says. The dimensions within the jets itself, within the channels, within the feed, also the nozzle itself. Material properties would be things like viscosity, surface tension, Young's modulus, density, things like that. Not only of the material that's in contact with the ink, but also of the material behind that, the laminates that make up part of the jets. And then function would be what we would probably more popular or used terms would be fire pulse width, drop velocity, drop mass, resonance response, frequency response, things like that. So our excuse me, our modeling software really only solves forwards-looking problems, and but the designer himself is left with really solving backwards problems, which is basically trying to equate the functions, so the fire pulse weight, the drop mass, drop velocity, etc., to materials properties of dimensions and things like viscosity, surface tension, things like that. So what ultimately we do then is we use the simple model to start with, and that is a backwards problem. So we would use equations like the mass of the drop equals 0.5 times the fire pulse width times the velocity at the nozzle times the nozzle area itself. And that's what we try and do, is to eliminate a lot of the crazy and unfeasible properties and dimensions to come down with a smaller design space. Once we do that, then we input lots of that into the proprietary modeling software that we have, and then this basically is running pretty much 24/7 to all intents and purposes, our servers, modeling tens, hundreds, thousands of runs. From then we take a couple of runs and we apply CFD, computational fluid dynamics, to that in order to get a couple of jet designs that we go forward with to build masks out of and build them into jets and physically test them in our labs in Dymatics. So almost there. Despite all that kind of simple jet harmonics that resonance circuits that we've talked about, in reality, jets, everybody's piezo jets, not just Dymatics, has real complexity. And what we're showing here again is pressure and flow at the nozzle after, as you can see, the fire pulse there in yellow is being applied to it, and it's a time at the bottom there. So here we can see, as we're retracting raising the piezo, the meniscus, as predictable, is descending, and the meniscus is retracting and it's relieving pressure. What becomes a little crazy at this point then is, for no apparent reason other than because the floor is still raised at that point, so nothing else is going on, the flow and the pressure actually start to change before the piezo was dropped. What this is a consequence of reflections that are going on within the descender channel itself. So these are creating pressure differences and ultimately flow. Now nothing is ejecting or is being jetted at this point. This is just similar to the concept of a tickle pulse, where you have energies that are being transferred to the meniscus, causing at the very small level kind of vibrations and fluctuations and pulses within the meniscus itself. This is the point then at where the piezo is dropped and the pulse, as you can see there, and the pressure pulse arrives at the nozzle itself, and then this is where the drop tail off is in relation to that. Then the rest of it then is meniscus bounce, more reflections going on there. So it's extremely complicated dynamic that's happening there during the raising and the dropping of the piezo and the subsequent seconds that happen after that. So as a review of my presentation then, what we've looked at is how the piezo inkjet works, a simplified model around circuit resonance that helps us allow inferences for predicting and troubleshooting jetting problems that we see in reality. The scaling down to the MEMS in order to get the smaller jets to get the higher firing frequency and performance challenges not just the MEMS portion of it, but the PZT portion of it. Our sputter PZT we consider, for the reasons I've outlined, to be a key enabler here in order to achieve the reliable performance at that scale. The simping model is a concept. It helps us debug, but in reality, as you can see, it's much more complicated than that. And we are thankful for our designers who spend hundreds of hours at this, losing their minds, becoming insane on our behalf, so we don't have to. Okay, thank you very much.